Alright, so to summarize that, this is what we have. For edge list, we've got big O of M, constant time on a few things, MMM, which makes sense because everything's stored in our M edges. For an adjacency matrix, n squared comes into play, and then we've got big O of n, which makes sense because we have an n by n structure. Adjacency list is sort of in between. So we have some operations that take big O of n, some that take big O of n, some that take big O of m, and then of course the memory usage depends on both. It's those added together, so whichever is bigger. So which is best sort of depends on your application. So it depends on the relationship between n and m. So if you have what's called a sparse graph, so few edges, a lot of times you want to go with the... That doesn't show up very well. Let me try different color. A lot of times you want to go with an edge list if you have few edges. If you have a dense graph, a lot of times you want to go with an adjacency matrix just because it makes access very easy. It's really easy to access any particular edge in constant time. So to check an edge, it's constant time. And then finally, this is sort of your generic data structure. So for this class, I pretty much always recommend using an adjacency list kind of data structure. And in fact, in a few assignments, I'll require you to use an adjacency list. Okay, so this brings us to your exercise for this set of slides. And this is a good time to revisit the friend circle algorithm from the very first class period. So I'm just going to put a sort of artificial pause here, give you a chance to look through that and see if you can solve it again. And then I'm going to give you sort of the shortest way that I could think of to solve this. Not in code, because this is going to turn into an assignment down the line, but just how do you solve the friend circles problem from a very high level kind of understanding. Well, as it turns out, the friend circle problem is giving you the input as an adjacency matrix. So you can think of that as, an n by n matrix where each true or false spot in the matrix tells you whether or not a given vertex is connected to another one. So let's call this vertex I, this one vertex j. Whatever's at that cell tells you if I and j are connected. And the idea is if you have a graph that looks like this, so let's say person A is friends with person B, and person B is friends with person C, then that's a friend circle. They're all friends. Now if you have another person over here, D, and maybe a third one, E, and let's say they're friends, but nobody is friends with F, you would have 3 friend circles. You would have friend circle 1, 2, and F by themselves in their sad friend circle. Well, maybe it's not sad. Maybe F prefers to be alone. So how do you solve this problem? I'm not going to give you pseudocode or give you code for this because this will be an assignment, as I mentioned. But essentially all you're going to do is call DFS a bunch of times. That's it. The friend circle problem is really nothing other than the connectivity problem. So you can call DFS, you can also call BFS. Either of those are going to work. You can also make up your own algorithm, let's call it RFS, and just go through the edges in random order as opposed to in a breadth first or a depth first search order.